last time, all right, so we did Joule and Joule-Thomson, which involved those really crazy mouse traps. And what it came down to is measuring, okay, this is Joule-Thomson, let me write down the Joule. It doesn't really matter. I usually, in terms of the mouse trap, which I'm not going to test you on, do you remember how Joule built the apparatus? I don't really care about those kinds of details. So these are really, in my opinion, just about the same thing. But remember, Joule expanded a gas, and the mousetrap was so odd that he managed to do it under conditions of constant internal energy. And anyway, so this was the result. And obviously, I've been saying quite a bit that internal energy does not change if temperature is constant. And I have to backtrack a little bit. That's true of a perfect gas. And so then they built and so this was very small and they couldn't measure it, so they tried again with a better mousetrap using enthalpy. The effect of enthalpy is greater than internal energy. Enthalpy tends to be greater, so changes in enthalpy tend to be greater. My point being is that the Joule-Thomson experiment was likely to result in a greater temperature change for the gas. It just worked better. And so they were able to get that finite temperature reading to read something. This one didn't because, again, yeah, this ought to be small. And it is, but it's not zero for a real gas. You're going to do derivations of this. And actually, after the test, you're going to derive that this is either zero for a perfect gas and not zero, and you'll use the van der Waals equation. Now, whenever I see enthalpy and internal energy, they always are doing basically the same thing. It's just I take my U's, I put H's, okay, that's a given. But I take my V's, I take P's. Often there's a minus sign because P and V work opposite of each other. Anyway, blah, 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 blah. Now, in terms of the effect they measured, notice that this has everything to do with refrigeration. This is a gas expands. Does it get cold? These things do. Notice that Freon gets very, very cold, but unfortunately the Freon is a chlorofluorocarbon, which was destroying the ozone layer, so we don't use that anymore. I don't really know what modern refrigerants are. And before we were using Freon or whatever it is we use now, we used ammonia. There is nothing more dangerous than compressed ammonia. So the very first refrigeration, seriously, there's a railroad called the Erie, Ohio Mobile. I grew up in Mobile, Alabama. I'm sorry that you have a very hard time understanding me, but but the railroads used to actually collect Lake Erie ice and ship it down to Mobile because, seriously, there was no other way to get ice. And my grandmother had an old ice chest, so every week they'd get a huge block of ice. All right, but instead people figured out refrigeration from this kind of stuff, and they used ammonia in these factories in cities. Because ammonia has a very, the fact that this number is relatively large means that ammonia cools when it expands, and you can use that to make ice. The problem is compressed ammonia will explode with really little provocation and kill hundreds of people. We know that because that's what happened. And so Freon works much better. You can use less of it. It tends to be a little less explosive. Actually, there's a movie called The Mosquito Coast. Anyone seen that? Oh God, it's actually worth looking to download it, right? Oh, I said that on camera. Anyway, when Harrison Ford, when he got real popular after Indiana Jones, this was his first art house movie, and it's about a guy who rejects modern society, goes to the Amazonian jungle on the Amazon, and he does that to make a simple life. But what he ends up doing was he recreates modern conveniences. He basically goes back to what he used to have. He builds an ammonia refrigerator because, hey, why not? The ice is kind of awesome, especially if you don't ever have it. Ends badly. I don't want to say anything more about that, but it is worth watching. Now, here's another thing I want to just give you a little hint on your homework. That is that it is true that the magic cylinder that I'm always telling you about, if I compress a gas, it will get hot. If I expand the gas, it will get cold. And you know that, you don't need to write this down. TF over TI is, I always remember this. You don't need to remember this. It's on the cheat sheet. And I hope I'm doing this right. I should double check this. Anyway, notice that this predicts that a gas expanding always gets cold. And I really do need to check whether this is correct or not. I'm pretty sure this is correct. Yeah, this is correct. This is correct. Here's the thing that's a little funky here, is that I was telling you yesterday that helium and hydrogen, if they expand, they actually get hot and everything else gets cold. But this equation says that everything expanding gets cold, whereas I had said right here, but these would get hot, but these say they get cold. Notice that there's no stipulation that this doesn't work for hydrogen or helium, right? So this is your homework. Why does this say hydrogen and helium get cold when I told you yesterday they got hot, right? How can they both be correct? And let me give you a little bit of hint of an answer. Remember, this is the magic cylinder, right? Was this the magic cylinder? It was a magic cylinder. Was it the magic cylinder? You remember the Joule-Thomson device, the crazy mousetrap? Was that the same mousetrap? No, they're still cylinders, but this device is a little bit funkier than this one. So it is still true that gases expanding will get cooled. It just depends on the mousetrap that they're in. Because these guys they did really a heck of a lot of engineering to make this work the way they did. And it's like two magic cylinders, not one, right? And this is just a magic cylinder. Anyway, I don't want to give you, I'm about to give you the answer, and I know I'm about to give you the answer, so I have to stop. Because I want you to think about it. Because that's a hell of a thing, isn't it? Right? You just saw that I told you hydrogen and helium expand and get hot in the Joule-Thomson device, but I also just derived an equation last week, I'm just reminding you, that said that they get cold. So please reconcile that. Okay, so now we're skipping to chapter 5. Is anyone reading? Anyone? No? Well, remember, policy is, if I didn't say it, or if it, look, there's a lot of handouts, by the way. I added some more handouts. I'm going to add more handouts right when I get back on these double lectures. So we're on chapter 5, and this is about heat. A little bit more about heat, and I'm going to prove it is inexact. So let's prove it, and remember that's Euler's criteria. I'll remind you in a moment. And remember that heat is path dependent, and as I told you before, I'll show you this in a little bit, not today or not this week, but next week. If this is path dependent, the paths are of course reversible and irreversible. And reversible heating is efficient heating. Irreversible heating is when the fire under the magic cylinder, some of the heat obviously kind of wafts away. That would be irreversible heating. Anyway, so I want to prove that heat is inexact and path dependent. And to do that, and now remember, we're going to do a derivation, and this is a very difficult one, by the way. It's very challengingly hard. So I could not do this spot on. I've done this 10 years. And if you were to ask me, like a month before class began to do this, I could do it, but it'd take me a couple of tries. So this is a difficult one. Just so you know that, yeah, this is not easy. Okay? So I'm about to prove that heat is inexact, and we're going to do dF, dx, and all that jazz. What do I want to say? Okay. Using 6th grade mathematics, I'm going to isolate heat, and that is U minus work. Okay. Now, this is the part where, again, this is why this is not on a test. This is why I don't think I can answer it spot on myself. I need to start whittling things away, and I'm going to have to do those derivation. I'm starting a derivation. I have to do another one and then insert it back in, like what I did with CP minus CB, if you recall. So that's how. You really would have no idea to do this and how to do this. So I'm going to have to figure out what the U is. Of course, I know what are the proper variables to let change. I have to know that they're volume. Of course, I have to hold something constant. I choose temperature. Again, I could have expanded the change in U with anything. I know to pick V and T because I already know the quickest way to answer the question. You could have picked pressure, and actually entropy would be the other thing. Let's not worry about that. You would get the right answer. It would take forever to do so. This is much faster. Now remember, I held T constant, so now I need to let it change. Of course, V changed, now V is constant. And remember, those are just the mathematical rules of how functions change. And I'm going to go ahead, just for convenience, I'm going to go ahead and just wipe, let me make sure I'm doing this right. I'm going to go ahead and just wipe this guy out, and that's because of the constant heat. Just for convenience, I'm just going to wipe this out. And so now what I want to do is, heat is the change in U, change in T at constant V, dt, minus the work. Now, again, work is formally minus exterior pressure, change in volume, but I'm going to go ahead and say that this is reversible heating. Now, remember, minus minus is plus, don't get confused. I've decided to examine what I plan to examine on the reversible path because I can, because this, again, will make this derivation easier. I can choose how to do it. I will choose the easiest way. I could have made it irreversible, and I would get to the same answer. It just would have taken me an unbelievably longer amount of time to do so. There's no value in that. So anyway, all right, so I'm doing it this way just because I can. And now what I want to do is, before I switch to another board, I want to map this into my equation, which you are hopefully kind of sick of, which I would actually prefer that you're sick of it for reasons I've already said. If you're sick of it, it's because you know it so well. This is, again, the multivariable change in the function f. Okay, I want to map these onto each other because I know the formula, which is in your cheat sheet, for Euler's criteria, whether something is exact or inexact. Okay, again, here's a little aside. I need to, again, I've got all the formulas in the cheat sheet. I just need to define what f is, and that's obviously Q. No. Q is Q. Now I know what you got confused, and I'll speak to that in a second. Hold on, let's do x and y. X is T, right? Okay, and y is of course V. Now what got you confused there is actually because you tried to do this to this. No. df dx, a constant y. This is what you actually wanted to do. Now remember that this is the change in heat with respect to temperature at constant volume. It's equal to the change in U with temperature at constant volume, and that makes sense because U at constant volume, there's no work, so U should be heat. So that makes sense. But let's not worry about that for right now. Let's just do it this way. And df dy at constant x is equal to what? Now we've already identified y as v, so df dy at constant x, which is of course dq dv at constant t, but what is it? Remember these are, it's what?
dnRT over.
No, this is really simple. Wait, okay. Here, I set them equal. X is t, this was v, this is P, right, geez, look, it's E, you are making this way too hard, right? Now I can tell you this, on tests, you will get the questions, the derivation questions wrong because you made it way too hard. The point of this is to make this the same as that, and I've done that, okay? Again, easy, do not overthink this. This is just fill in the blank, essentially, right? Okay, now I'm going to do the Euler criteria, and I'm going to show that it fails. And then I'm going to make a modification. And don't forget that anything that is exact is actually a state variable, like U is a state variable. Like, U and H are state variables. They only care about their endpoints. They're not path dependent. Anyway, I'm rambling. Okay, so with this, let me remind you, actually, I thought of a new way of doing this. I've been doing this for years. I just thought of a new way of doing this. Okay, so now I'm going to use the Euler criterion. I'll just write that down in a second. Now remember the Euler criteria says, okay, you've got the change in something is that change exact or inexact? And the way you do that is you've got a derivative. Now notice that I'm doing this here to here. You do double, you probably forgot, or some of you remember, but some of you forgot, whatever. The Euler criterion says, take that thing and do a double derivative, and then permute the order, and see whether they're the same. And yeah, I know that these constant dealies are a little bit painful, but okay. Anyway, and I've written it this way so that you can kind of just, this to here, right? It's a little off, but anyway, you know that this is P, this is du dt, a constant V. Okay, so now what I need to do is evaluate each one and see whether they're the same, right? And now remember, this is the Euler criteria. This has not been derived. This has been stipulated as the Euler criteria. If you don't recall, this is again, if this is true, then this change is exact. It's an exact partial versus inexact. And I talked about this on that first extra hour on our first Friday. And I told you it was going to come back. Okay. Regardless, even if you don't remember, this is what it is. And it's on the cheat sheet if you need it. Okay, let's do this guy. Okay, y is what again? What? V. Okay, and df dx is du dt. Then I have constant x, which is t. Okay. And it's equal to, let's not worry about it. Let's just finish this guy. Okay. Now, this is where, again, this is kind of funky. And I know that you would not come up with this off the top of your head. But change in u is exact. U is an exact differential. And I know that because I can express the change in U as the change in heat and the change in work, and the change in heat and work balance each other out. Even though those are path independent, you add them and now the result, the change in U is path independent, U is exact. I also know that that means I can write U is equal, not the change in U is equal to, but U is equal to, that's the equipartition theorem, 1/2 RT per degree of freedom. So that's definitely true. Okay, so the change in U is exact, and therefore I can use Euler's criteria. In other words, I'm going to flip the order of differentiation. See what I did? dv dt, now it's dt dv. There we go. Now that means that these dv's switch as well. So what's this? I'm just working down, by the way. So here to here to here. I'll toss it up here in a second. What's this?
0.
Yeah, 0, right? Right here. Okay, it's 0. Again, now, I'm sorry, I know I just went blah, blah, blah for a perfect gas versus a real gas. Yes, I know. But I've already made the stipulation that I'm using the perfect gas up there. I'll tell you a little bit how a real gas would be different, but so anyway, I've made some stipulations. I made it reversible. What else did I do? Yeah, I made it reversible. I stipulated up there that I would let U be 0 with change in T. So I'm going to do it again right here. Yeah, you see, yeah, I've already used it. I've already done this. So, and I'll tell you a little bit about how it's different if it's a real gas. Okay, this side. Okay, now X is what again? T. Okay, df dy constant X is P. All right, now that goes here. In case that's a little confusing, if you're not comfortable with this terminology here, remember that since these are all where you're in kind of unfamiliar territory, is that instead of X's and Y's and Z's and F's being exactly just that, in here they actually mean something. So this is a thing, and that thing hops right here. That's just mechanically how this works, right? Okay, so this is P, and the P hops on top, and a constant Y, and Y is V. And you may have realized I just did this. I've already stipulated that I am working with the perfect gas, which is nRT over V. And this is one of those times where it doesn't matter what's held constant. Regardless, this is nR over V. Sorry. Here, I'll toss this up in a second. Okay, NR over 0 is equal to NR over V. Huh? Is that okay? Right, of course it's not okay. NR over V is probably a pretty big number, and 0 is not. Okay. So there you go. If you're having trouble seeing it, there's the whole derivation, starting from Euler's criteria. Okay, yeah, kind of painful, I know. I'm well aware, I just did it. I told you I could not do this myself. If you asked me just off the top of my head, I could do it after a couple of tries. I've done this 10 times. Hey, finally I helped myself. So yes, heat is inexact because the Euler criteria has failed. Now I know that I blabbered forever about how real gases are different from perfect gases, especially when it comes to changing U with respect to V at constant T. All right, so it's not true that it's exactly 0. So what would happen is, if I use the van der Waals equation versus PV equals nRT, what you end up with is not 0, but a number like the Joule-Thomson coefficient. It's something that's like tiny, 0.0001 something, which would still not be equal to NR over V. So this works. It still works. I just made it, I just used a perfect gas because it just makes it a little bit dramatic and a little bit easier to write and a little bit easier to see. So the point is that the change in heat is inexact, and that's really that. Okay. Now the question I have, and I've already been telling you this, is what about this? What if I took heat and divided it by temperature? While you're looking at this by saying, well, I don't know, so what? Here's the so what. If this magically becomes independent, it is a state variable. And I've already told you what those are. Those are the energy functions. That would also be entropy. The thing that we haven't really said a lot about, you saw it in freshman chem and just kind of said, okay, the entropy, whatever. Entropy has everything to do with the second law. This class is 2/3, 66% of this class is about the second law. So this gives you a little bit of a hint what this is, right? Okay, again, the point is this weird, this slight perturbation to heat, would this be exact or inexact? So to do that, what do I want to do? Okay, so I'm going to go ahead and assume that you can, just follow along well enough. Okay, now let me write down what I did before, because I don't want to go through that whole rigmarole again. Okay, so I had the change in Q was the change in U, which turned into this, and then I did a reversible work, and so there's minus the reversible work, minus plus. Okay, so again, we were here just a little while ago, so I'm going to divide by T. I'm just going to divide by T. That does that. All right, now let's do an Euler criteria analysis. And to do that, so let's do this side, which I already know is going to turn into change in volume, 1 over T, du, dt. I'm just slipping a T into what you already did. So better make sure that's correct. Yeah. So I'm doing what we already did. There better be a change. Yeah, it's right up there. It's right up there. Yeah, right there. There you go. Okay. Let's go ahead and do this side. I have the change in P over T. Over T, a constant. Change in P over T with respect to T, a constant V. Okay, now this one, here, let me just go ahead and do this because this is just way too easy. This is the change in NR over V with respect to T. Again, this is one of the times it doesn't matter. And this is 0. Okay, now this one, let's get back to this one. This is kind of funky because remember, this stands on its own. It's actually, you know, technically this is heat capacity at constant volume. I didn't know if you noticed that, but I didn't want to confuse you with details. But it's technically heat capacity at constant volume. Now it's been multiplied by 1 over T, but notice that the second derivative is a constant T. Now, you would not have spotted this, and you're not familiar with multivariable calc. I know that. I'm telling you that since this is done, and this derivative is done at constant T, you can actually do this. You can bring it out. Because it's a constant, it's the number 5. Okay, and notice that I am now left with the exact same thing here. I'll just bracket that, so hopefully you put some notes in there saying that you already know what this is. It's 0. 1 over T times 0 is still 0. 0, 0, snake eyes. All right, so therefore, not using the board super well today. The change in heat over T is exact. There you go. What do I want to do with that? Yeah, that's just about it. What else is this called? Does anyone know what this is? I already said it a minute ago. What's this thermodynamic function? Yeah, entropy. And also, let me tell you that, okay, we give that the letter S. And now remember that I was actually using the reversible path. So let me stipulate that entropy is the change in reversible heat over temperature. That's kind of important. Now the reason that that's kind of important, I will probably not ever put this on a test because this really is a detail, that entropy is a state variable. I just proved it because it's exact. The change in S is exact. And I just did something really stupid. This is the change in S. This is the change in S. It's the change in heat over temperature. This is a state variable because it is exact. I just proved it. So again, entropy is a state variable. It's defined as the reversible heat over temperature. The reason that it needs to be reversible is, for one, I did the derivation that way, but that's kind of trivial. That's a smart answer, smart alecky answer. The reason is that for this to be path independent, the heat has to be path independent too. You snarkily get around that by choosing the path ahead of time, and you choose the reversible path. Anyway, that's the definition. Regardless, entropy is all about the second law of thermodynamics, which is the hardest thing that we cover in this class. And the first law, that energy cannot be created or destroyed, which I don't know if I've spelled that out yet. I just kind of assumed you knew it because you've probably heard that since you were very young. That kind of bit of, like equals MC squared, you've heard that. The second law is so complex, it actually comes in 2 forms. So let me write that down. Second law. Definitely entropy stuff is on the exam. Count on it. It's absolutely on there. And don't write this down. I just wanted to preview because you've heard this one. The second law states that entropy always increases. We're getting there. We'll do that in about a week. There's a second way of saying the second law, and I'm actually going to begin there, which is that you can't turn all heat into work. Okay, that's the Clausius form of the second law. Don't write that down. I don't care. I know that because I've taught this 10 times. But anyway, this is the other way of stating the second law, the one you probably have not heard. I'm going to begin explaining the second law with this because it's a little bit easier. Later we get into entropy always increases. Again, shelve that. We'll get to that next week after next, I guess. But this is really about the most important thing I can cover. Can't turn all heat into work. And what do I want to say about that? Let's see. So this is ultimately why engines are inefficient. If this wasn't true, then any engine you could ever build would work perfectly. All the combustion energy would drive the car down the street. And that another way of saying that is that You turn on your car, crank it up, go where you're going, stop, and you put your hand on the hood, it would be room temperature, right? So the fact that that's not true and that you should not do that, it'll burn your hand off, that is actually because the engine is not perfectly efficient, and some of that burning energy was turned into heat, and that's why the hood of the car is hot. If engines were perfectly efficient, if it wasn't for the second law, that all of that energy would have driven you down the road, so there's no energy left over to make the hood hot. And that'd be nice because you would have used less gas, but it's just not true. Let's see. Now, notice that this seems contrary to another statement I could make, which is that at constant T, the change in U is 0, and therefore, work is minus the change in heat. Okay, I just said the second law, the most important thing ever, this is why the universe is turning to hydrogen. This is why all life will come to an end. Oh, sorry, I don't mean to be all dramatic, it's actually true. This is why all life will come to an end everywhere. Even the aliens, you're gone too, because of this, and yet I just starkly violated it, right? The minus, it's because of the minus sign. No, minus just says left versus right, compression versus expansion. Nature doesn't know minus signs, right? This says work and heat are equal, and I just said that everyone in the whole universe dies because that's not true. That's a conundrum, right? Okay, so I don't know. Normally I'd say, well, what's the answer? But then I'd hear, the answer is that I remember how I do these questions, the magic cylinder. And I said, okay, the magic cylinder, I press on the magic cylinder and yada, 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 and I do some work, and there's some heat, and if it's isothermal, the heat comes out. Now this is actually really, you gotta be careful about the language here. I started with heat or work when I did this question. You know, I pushed the cylinder, and blah, 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 heat and work. What started, heat or work? Work. I started pushing on the cylinder. Right? And you know that motion is always a form of work. Motion turns to heat eventually. If I bounce a ball on the floor, that bouncing, motion is always going to be translatable into some form of work, right? Just like that question where the power plant cylinder is stuck and there's no work done, right? Because nothing's moving. Something moving means work's being done, but the ball keeps bouncing, and that's a gravity work. I don't know, whatever. It's work. It bounces less and less and then stops, and now there's heat. The ball is now hot. Barely, you could barely tell, but if you had a really nice thermometer, I'm sure you could tell that the ball actually warmed up a bit by bouncing on the floor. All work gets turned into heat. That's true, and you know that, right? Your car drives down the highway, and of course it's fairly burning hot. You shouldn't even touch the hood. And all that work is turned into heat. But you can't turn all heat to work. See, the point is, it's directional. Right, the second law is direction. I can turn work into heat, but I can't turn heat into work, and that sucks. Because it'd be fine if we rode bicycles to work, and we soon will when we run out of oil. But our modern society, our system of energy distribution begins with a burn, not with a work. We burn first and try to get work later, not the other way. That's just practically how we built our civilization. And if it wasn't for that sucks because of the second law that says that you're going to lose some, right? It sucks that your car, you didn't buy a car just to turn it into an oven. I mean, you could do that. It's actually not hard. I once saw a car catch on fire. It was pretty cool. It was cool because they got out in time. Seriously, the car was on fire. There were still people in it, so they got out in time. But you don't need that, right? You already have an oven at home. You want that car to turn all that gasoline entirely to work and only work, and if it doesn't do that, you had to pay more to do it. And you know that it doesn't do that, and that kind of sucks. It costs you more, but why? So that is the point of the second law. Now, unfortunately, I spent a lot of time explaining